All right, hopefully this will be a lot easier to read now that I have a document camera. So this should be hopefully just like we're in class, only not as fun because I don't get to talk to you guys. So anyway, we're going to do our last section of chapter 6. What we're doing is we're going to take a binomial problem. So back in chapter 5, we learned about binomial probability problems. For instance, if you roll a die 10 times, what's the probability of getting a 6 3 times? Something like that. So this is just a review of what the binomial distribution has, a fixed number of trials. So again, roll a die 10 times. And then the big one is that you can only have two outcomes, which are a success or a failure. We used this formula in chapter 5. We don't have to use it now, but I just put it there so we can remember what we need. So what you're going to need is you're going to need to pick out n, which is your number of trials. You're going to need your p, which is the probability of a success. And your q is a probability of a failure. You also are going to have to calculate your mean and your standard deviation. This is the best way to know that you're using a normal or the binomial distribution problem, is because in all the other problems that we've done in chapter 6, they give you a mean and a standard deviation. These will not, which you'll see obviously when we get to the actual problems. So the mean you're going to use for this is just n times p, and your standard deviation is the square root of n times p times q. All right, so you will have to calculate those two things to start every problem. Now, there's two things we have to take care of when we want to be able to use the normal distribution. So I'm going to grab my book quick. The problem with using the normal distribution is, remember, the normal distribution is a curve, and there's area underneath of it. So it's a continuous thing that, again, all the areas or the whole area is 1 and that sort of thing. What we have when we use the binomial distribution is binomial. If you remember back in chapter 5, making your probability graphs, we just drew lines straight up and down. There was no shading. So the normal distribution is representing a histogram where you shade in the boxes, but we need to use it for just lines. Well, there's no area of lines, so there's a couple of different things. Here's the first thing we have to check. If you notice, this is on page 339. These bars on the left-hand side are outside of the curve, and then on the right side, they don't touch the curve. They're underneath, okay? And then the one below it, they're all touching the curve exactly. So what has to happen in order to use the normal distribution for a binomial distribution is n times p has to be greater than or equal to 5, and n times q has to be greater than or equal to 5. I promise you they will always be this way, so you don't even really have to check it, but that is just a rule that you need to do. This next part is the really hard part to figure out, and I will say that you'll only miss a half a point on the test if you forget to do this. So most people kind of just don't even worry about it, but it is a little something you have to do. So here's what I'm talking about. When you have, and I'm not going to write the whole list out. If you want to copy it down from the notes that are on Canvas, you can, but I don't want you to think you should memorize that whole list of things. All right. Here's what I have. Here's what I want you to talk about. So this is our 0. Let's say this is my z-score right here. It doesn't even matter what it is. We're going to put A. Let's say I want to know the probability that my, I don't even need to do that. Yeah, I do. I want to know my probability that X, whatever I pick, is less than A. Okay, so remember I have to take my X and I have to calculate a z-score, which we'll talk about here in just a second. Well, here's what you have to think. Less than means this way. We don't know whether this is going to be in our shaded area or not, because again, we just have a bunch of lines going up and down. We don't actually have an area. So here's what you have to do. You want it to be less than this number. Okay, you want it to be less than here. So you need to make sure you do not count this. So what you have to do is you have to go a little bit below that one. So what you do is when you change your z, you're going to do subtract 0.5 from that number. Okay, and again, I know it seems really weird why to do that, and I probably can't explain it as good without being in person, but this is what you're going to do. Okay, so there's a whole bunch of different options, okay? But let's say this is my z value. I want it to be greater than. So the probability that x is greater than that number a. Greater than means we don't want to include this number. Okay, so this is actually our a value. We don't want to include this, so that means we need to be over here. So that means we are going to add 0.5 onto whatever our a value is. Okay, so it all depends on which direction you're going and whether or not you want to include it. So if you're less than and you don't want to include it, you need to go to the left. If it's greater than and you don't want to include it, then you're going to have to add 0.5 onto it. Now let's look at the opposite thing. What if I want less than or equal to? Well, this technically is always a less than. So less than or equal to, this means we do want this number. We need to include this line. So that means we need to go a little bit above it. So you're going to add 0.5 this way. All right, this one, if we're greater than or equal to. So again, we do want to add this line, so that means we need to go a little to the left. So now you're actually going to subtract. So you can't just say, oh, if it's greater than you add, or if it's less than you subtract. It depends whether you want to include the value or not. And again, the easiest way to do it is just to draw it out. There's one more thing. Sometimes we want to know if it's equal to an actual number. So we want to know if whatever we're going to pick is actually equal to. So the probability that x is equal to a. Well, you can't find the area of a line. So what you have to do is you have to go below and above. That's obviously really drastic, but you have to go above and below in order to make an area. All right, so this is going to be a minus 0.5 less than z less than a plus 0.5. Okay, so again, this is the big thing that you have to add on for this, but it's not a huge thing if you don't do it. All right. One last thing, go ahead up here. This one usually throws people off, but you're going to use this z-score. And the reason it throws people off is because from 6.3, we had a sample size, so we had to do the square root of n in the denominator. This one, you're going to have a sample size also because you're going to have your number of trials. All right, but we still don't actually use it. All right, so don't get too super concerned about doing that. All right, so I'll write that on this page also. This is the z-score that we're going to use. Z equals x minus mu over sigma. And it will be labeled in your formula sheet when to use this z-score. Okay, so here's how it works. A magazine reported that 6% of American drivers read the newspaper while driving. Hopefully none of you do that. If 300 drivers are selected at random, find the probability that exactly 25 say they read the newspaper while driving. Okay, so first thing I do is I write this. We want the probability that x is equal to 25. Okay, we want the probability that x is equal to 25 because it says that that's what it's asking us to do. All right, and then we need our mean. Our mean is n times p. Well, we're asking 300 times 6%. That should give you 180. All right, and then we need to do our standard deviation, which is the square root of 300 times 0.6, or you've already done that, you can make it 180, times then 0.94 would be your Q, and sorry, I just did 60% instead of 6%. 18 makes a lot more sense than 180. So again, if you remember, this means we expect 18 of our 300 people to say yes, that they read the newspaper while they're driving. And this is 4.1. Okay, so now it looks like the same problems that we did in 6.2. All right, you have your mean and your standard deviation and you have your x value. But here's the thing, is that since we want to equal to, that means what we have to do. So here's the thing, your mean is 18, your 25 is going to be over here then. So we want that to be our z-score, so we need to go around it in order to find the area. So we need to do, this is equal to the probability that 24.5 is less than z, which is less than 25.5. Again, since it's an equal to, you can't find the area of a line. So you need to make yourself a box in order to do that. So z equals 24.5 minus 18 all over 4.1. That gives us 1.59. Z equals 25.5 minus 18 over 4.1. That gives us 1.83. So again, 1.59, 1.83. I'm going to look both of those up. 1.59 gives us 9441. And this one gives us 9664. So 9664 minus 9441 gives us 2.23%. So very low percent probability that that's going to happen. That should make sense because, again, you only expect 18 people to say yes. We want to know the probability that exactly 25 are going to say yes. So first of all, exactly is always hard to do, and then we're way over how many we would expect in the first place. I'm going to have to stop it because I can only go for 15 minutes, so I will finish the other two on another video.